Well, good afternoon, everybody. Thanks for this opportunity to present our project, our R61 project. We call our project the Capture project, and I'll tell you a little bit about that and how we got to this project. Nathia has already done a great job of setting all this up because I was a postdoc in Nathia's lab for a couple of years and have started my own lab at the University of Utah. So it's really an honor to be here, and I'm excited to share some of our work. So as we all know, there are new opportunities for doing cognitive neuroscience in the wild, or neuroscience in the wild more generally, from eye trackers to GoPro cameras, GPS tracking on all of our phones, mobile movement tracking, and so forth. And then, of course, the development of the NeuroPace RNS, and specifically the ability to work with this as a research tool, as Nanthia has so pioneered in this field. And so she just presented some wonderful insights that have been developed from this really powerful device that allows us to pull data from the hippocampus or other parts of the brain at millisecond precision as people walk around in the real world. And when I joined the lab, I was really excited about this possibility of taking this technology into truly the real world, literally walking around campus. And so first, I'll tell you a little bit about some of the work that we've done to set up our project for the R61 grant. And then what we're going to do as our next step. So we wanted to translate, from the laboratory findings that Nathia and her team had discovered in terms of movement speed, walking around a room, and it's all equipped with sensors on the wall. And we wanted to put all those sensors on the person themselves. So we synchronized the NeuroPace RNS with multiple wearable devices that are, most of which are just purely off the shelf, from Raspberry Pis to GoPro cameras, things like that, and spent a couple of years trying to figure out how do we get all of these things to work together. And then we designed a navigation and memory experiment that really was aimed at trying to really move out of the lab into the real world temporal and spatial scales. And so we developed what we call the photon pack that allows us to do laboratory experiments, real world ambulatory experiments, and ultimately we hope to be able to do some real world augmented reality experiments with these types of systems in the future, at the scale of your daily life. And the reason we're interested in this is we know that autobiographical memories are really actually formed during freely moving behaviors and at the temporal and spatial scales of life. Often our memory experiments are relegated to a laboratory setting where you're looking at pictures or something like that, or in the terms of autobiographical memory, all we can really do is measure what you remember from your past without actually having captured any sort of veridical recording of what you actually experienced during those times. And so we want to be able to capture autobiographical memory encoding and then also test what happens to the brain as you retrieve those experiences. So this UCLA system included the sort of RNS research tools, the Raspberry Pi, movement tracking on the lower limbs of the body that allows us to get their gait and their movement speed at really fine precision. We also had a phone that we developed an app for that allows us to pull internet sort of clock times that synchronizes devices across different internet connected phones, and we can use that as a baseline sort of foundation on which to build other types of synchronization, from flashing lights in front of cameras to dropping accelerometers at the same time, and so forth. And so we developed this system. It was, we're still using this now and still collecting data with this now. And so the task we designed was a task where we have patients walk around the UCLA campus. It's about a 3/4 of a mile route. And all we were asked them to do was the most naturalistic thing that we could think, which was learn and navigate the route the best that they possibly could. So we taught them the route by just walking next to them and pointing. We had different landmarks that we didn't tell them anything about, but we looked to see if their eyes fell upon them with eye tracking. And then we also had them do 6 to 7 navigation walks where they navigated themselves around this route around the UCLA campus. And so far in that data, we collected this sort of preliminary data. We collected 5 participants and about 30 miles of human hippocampal recordings as people navigate through the real world. This is some of the eye tracking data that we can synchronize down to the saccade with the brain data. And we get this really, really nice precision of, being able to pick up on exactly what they're paying attention to and so forth. One of the challenges of all of this is that in real world behavior, you have to annotate all of this data. And so this is one of the things that I'd like to bring up to discuss today is tools that can be developed to annotate video data from behaviors. If we're going to be looking at real world behaviors, it's often not the case that we can have trial-based, experiments. And so this has been something that my lab has developed in MATLAB. It's been really challenging, and it's taken a long time. And of course, AI can really step in to help us with some of this, but can't tell us everything. And so I'd like to talk a little bit about what we can do with AI. So you can use AI models to pick out what's in the environment, and when there are collisions of eye tracking with those objects, we can segment all of these different objects in different ways. And we can also use large language models to kind of pick apart what is actually happening in the videos from the model's understanding. And we're working with computer scientist Luis Garcia here at the University of Utah to help us try to figure these sorts of problems out. We've also developed other insights, like looking at what happens in the brain when you're indoors versus when you're outdoors, which is difficult to do even when you're in doing animal studies. We find that there's this low frequency activity that changes as a function of being outdoors, that it's stronger when you're outdoors, between 5 and 12 hertz, which is an interesting insight that we can take advantage of in the future. So that tells us something about how the brain responds to different contexts that we haven't been able to report in before. We're also able to synchronize all of this data down to the sampling rate of each of these devices. We can capture things like velocity, fixation percentage, and LFP data as they navigate through indoor and outdoor environments. We can align that data to different behaviors, like when patients get lost. This is one of the behaviors I was really interested in. And so this is eye tracking data where 100% here is where you're staring at something, and 0 is where you're looking around constantly. And as you can see, when you get lost, you have this big drop in this number, which suggests that you actually start looking around trying to orient yourself. That's the first thing that happens. And then that actually seems to happen before you actually get any brain changes in the anterior hippocampus. Then you slow down, you slow your behavior, and then turn around and start to speed back up again. And in fact, you actually see these changes as the patient sort of starts to go the other direction and starts to correct their behavior. And then finally, we can also even measure things like skin conductance as a measure of arousal to see what changes and when do those changes happen relative to the changes in brain activity. And so we're really excited about these sorts of findings and are writing this work up now. The goal of our capture project will be to build a smartphone-based recording application that will shrink down all of our different separate devices into one app, these synchronized wearables, and synchronize those with invasive neural recordings during real-world behaviors like autobiographical memory encoding. And our overall aim is to develop this application that will ultimately capture a range of real-world cognitive processes, from attention to social interactions and so forth, at the temporal and spatial scales of human life. And finally, in the R33 phase, we'll, as long as we meet our milestones, we'll demonstrate the capability of our application to accomplish autobiographical memory encoding recording in 10 participants as they navigate through places you would go with your friends and family just to make memories, like gardens, parks, aviaries, and aquariums. And we'll be working with neuroethicists to make sure that we deal with privacy and all those sorts of things. So this is just kind of schematic of how we plan to sort of shrink this. So we'll be going from all of those other devices to one phone, and smartwatch and eye tracking glasses, paired with hopefully the sort of flexible coil that Nantia just discussed, and some other tools that will allow us to observe the recordings that we're capturing as they're walking around in these real world environments. We've started a partnership with a developer of an app called the Sensor Logger app, which has a lot of the capabilities that we're looking for. That person has come on our team as the app developer for the new Capture app. And they'll be taking their baseline app that they already have and pairing and bringing in the eye tracking synchronization and the smartwatch synchronization for skin conductance and heart rate. So we'll be working on that, as well as subjective sort of scales. This is our team. We are a team comprised of 3 different universities, from Utah to UCLA and Duke, and what will be Duke, and then Utah Computer Science and UCSD. We've started to really fill out our team, and we're really excited about the people that we brought on to the team, from the postdocs, graduate students, and engineers. So I'd like to thank you all for your attention. This is my crew here at the University of Utah, and we have a great team, of which none of this would be possible without the incredible pioneering work from Dr. Sutana's lab and all of the things that all of their team has taught us. Thank you so much.